Hi, I'm Mike Paulden, an assistant professor at the School of Public Health at the University of Alberta. Over the next 10 minutes, I'll be answering the following question. Are the equal value of life years gained and health years in total approaches viable alternatives to the QALY? Matters of logic and matters of value. Before I begin, I have some acknowledgements to make. I'd like to credit my co-authors, Tristan Snowsill, James O'Marney and Christopher McCabe. I'd like to thank Ken Bond for providing feedback on an earlier draft of this work. This work was conducted at the University of Alberta, and the University of Alberta respectfully acknowledges that we are situated on Treaty 6 territory, traditional lands of First Nations and Métis people. No funding was received for this work, and I have no relevant conflicts of interest. Let's now start with some background. The Institute for Clinical and Economic Review, or ICER, recently published its Value Assessment Framework, which supports ICER's valuations from a US payer perspective. In addition to cost per quality adjusted life year, or QALY analysis, ICER also considers cost per life year and cost per equal value life year gained. The equal value life year gained is intended to address a specific issue with QALYs, the potential discrimination against those with poor health-related quality of life. Yet, the equal value of life year gained has its own issues, such as undervaluing life-extending treatments that improve health-related quality of life. Coinciding with ICER's publication of its value assessment framework, Basu and colleagues recently proposed an alternative approach called health years in total. The authors claim that the health years in total approach overcomes both issues above and may provide a viable alternative to the QALY and the equal value life year gained. The purpose of this presentation is to consider whether the equal value life year gained and health years in total approaches are viable alternatives to the QALY. First, we will consider how each measure is calculated. Then, we will consider matters of logic. Does each measure satisfy two basic axioms of decision theory, independence and transitivity? Third, we'll consider matters of value. To what extent does each measure satisfy a set of potentially desirable properties? And we will end with some conclusions. Throughout the presentation, we refer to a hypothetical example. There are three treatments, X, Y, and Z. X provides a life expectancy of 1 year with a perfect health-related quality of life of 1. Y provides a life expectancy of 2 years with a reduced health-related quality of life of 0.6. And Z provides a life expectancy of 4 years but with an even lower health-related quality of life of 0.2. Let's now calculate each measure. Calculating QALYs is straightforward. The life expectancy for each treatment is multiplied by the health-related quality of life. The area of each region on this figure therefore represents the QALYs for the corresponding treatment. Alternatively, we could plot this on a bar chart where the vertical axis represents the QALYs. We'll use this format from now on for ease of comparison with the other approaches. Calculating life years is even simpler. Under the life year approach, the value placed on each year is 1, regardless of the health-related quality of life. So we can plot this on a similar bar chart where the vertical axis now represents the life years for each treatment. Now let's calculate equal value life years gained. The equal value life years gained measure uses QALYs to value each year up to the life expectancy with current treatment, then uses life years to value each year beyond this time point. The key point is that the equal value life year gained for each treatment depends upon what is considered current treatment. First, suppose X is current treatment. Since life expectancy with X is 1 year, the first year of life expectancy for every treatment is valued using QALYs, then life expectancy beyond 1 year for every treatment is valued using life years. Since X provides 1 year of life expectancy, it's valued using QALYs. Since Y provides 2 years of life expectancy, the first year is valued using QALYs and the second year is valued using life years, for a total of 1.6 equal valued life year gained. Since Z provides 4 years of life expectancy, the first year is valued using QALYs and the following 3 years are valued using life years, for a total of 3.2 equal valued life year gained. Again, we can plot this on a bar chart, where the vertical axis now represents the equal valued life year gained for each treatment. Since the QALYs and life years components are summed, these are stacked on top of one another in this bar chart. Now suppose that Y is current treatment. Since life expectancy with Y is 2 years, the first 2 years of life expectancy for every treatment are now valued using QALYs, then life expectancy beyond 2 years for every treatment is valued using life years. Since X provides 1 year of life expectancy, its value is unchanged as it was when X was current treatment. Since Y provides 2 years of life expectancy, it is now valued using QALYs only, for a total value of 1.2 equal valued life year gained. Since Z provides 4 years of life expectancy, the first 2 years are now valued using QALYs, and the following 2 years are valued using life years, for a total of 2.4 equal value life year gained. Again, we can plot this on a bar chart. Note that now that Y is current treatment instead of X, the second year is now valued using QALYs rather than life years, lowering the value assigned to Y and Z. Finally, suppose Z is current treatment. Since life expectancy with Z is 4 years, the first 4 years of life expectancy for every treatment are now valued using QALYs. Since 4 years is the longest life expectancy of any treatment in this example, this means that all treatments are now valued using QALYs only, such that the equal value life year gains measure is equivalent to the QALY. Finally, let's consider how to calculate health years in total. This measure is built on the notion that life years gained provide distinct utility to individuals from the health-related quality of life gains, and that these utilities are separable in nature. This requires the following conditions. First, the utility from life expectancy must be independent of that from health-related quality of life. And second, the utility from health-related quality of life must be independent of that from life expectancy. This second condition is problematic, since it requires that health-related quality of life be considered over a common life expectancy for all treatments, regardless of the actual life expectancy for each treatment. Now, this cannot be done without either 1. Omitting QALYs for treatments with longer life expectancy, and or 2. Inventing post-death QALYs for treatments with shorter life expectancy, both of which are problematic. The health years in total approach considers health-related quality of life over a time period corresponding to the maximum survival under any given alternative. This requires inventing post-death QALYs based on a counterfactual post-death health-related quality of life for all treatments with shorter life expectancy than this maximum. Let's see what this looks like in our example. Here, the maximum survival is 4 years with treatment Z. We must therefore calculate what the authors call modified QALYs over 4 years for all treatments. Since X has a life expectancy of 1 year, we must therefore invent post-death QALYs over an additional 3 years. Since health-related quality of life with X is 1, this results in 3 post-death QALYs in addition to 1 actual QALY. Since Y has a life expectancy of 2 years, we must invent post-death QALYs over an additional 2 years. Since health-related quality of life with Y is 0.6, this results in 1.2 post-death QALYs in addition to 1.2 actual QALYs. Finally, since Z has a life expectancy of 4 years, we do not need to invent any post-death QALYs for Z. Since health-related quality of life is 0.2, there are 0.8 actual QALYs only. The health years in total for each treatment are then calculated by summing the life years, actual QALYs, and post-death QALYs. So in this example, the health years in total for X are 5, comprising 1 life year, 1 actual QALY, and 3 post-death QALYs. The health years in total for Y are 4.4, comprising 2 life years, 1.2 actual QALYs, and 1.2 post-death QALYs. Finally, the health years in total for Z are 4.8, comprising 4 life years and 0.8 actual QALYs. Let's now move on to matters of logic, and our question is, does each measure satisfy 2 basic axioms of decision theory, independence and transitivity? Independence requires that if A is preferred to B out of a choice set AB, introducing a third option X expanding the choice set to ABX must not make B preferable to A. So for example, suppose that a woman is offered a choice between apple pie and blueberry pie and chooses the apple pie, and a few minutes later the choice set is expanded to include cherry pie. The woman should not then switch from apple pie to blueberry pie. Transitivity is a relation between three elements such that if it holds between the first and the second, and it holds between the second and the third, it must necessarily hold between the first and the third. For example, if 1 is smaller than 2 and 2 is smaller than 3, it logically follows that 1 is smaller than 3. We find that QALYs satisfy the independence axiom. In a pairwise comparison, if y has greater QALYs than x, introducing z does not change the ordering of x and y. The QALY also satisfies transitivity. If y has greater QALYs than x and x has greater QALYs than z, it necessarily follows that y has greater QALYs than z. Life years also satisfy the independence axiom. Introducing z makes no difference to the ordering of x and y. And life years satisfy transitivity. If y has greater life years than x and z has greater life years than y, it necessarily follows that z has greater life years than x. Things get more complicated when we consider the equal value life years gained. For any given current treatment, this approach satisfies the independence axiom. Introducing z makes no difference to the ordering of x and y. Also, for any given current treatment, this approach satisfies transitivity. For example, if x is current treatment, then y has greater equal value life year gains than x, z has greater equal value life year gains than y, and it necessarily follows that z has greater equal value life year gain than x. However, a vicious circularity may result if comparisons are repeated following changes in current treatment over time. Suppose that x is introduced first. When y is introduced later, it's compared to current treatment x, and since y has greater equal value life year gain than x, y is adopted and replaces x as current treatment. Suppose z is then introduced and compared to both x and current treatment y. Since z has greater equal value life year gain than y, z is adopted and replaces y as current treatment. The problem is that if this analysis were to be repeated sometime after adopting z, we would find that y now has greater equal value life year gain than z, so y would be reinstated as current treatment. Yet if we repeated this again, we would find that z now has greater equal value life year gain than y. Using the equal value life year gain to determine current treatment may therefore result in a vicious circularity. Things get problematic when we consider the health years in total approach. This violates the independence axiom. In a comparison of x and y, y has greater health years in total than x. Yet if z is introduced, then x has greater health years in total than y. The health years in total approach does satisfy transitivity, but only if the maximum survival under any given alternative remains fixed across pairwise comparisons. This requires that survival with z be considered even in a pairwise comparison of x and y. If that pairwise comparison were to be independent, the health years in total approach would violate the transitivity axiom. Here we would find that y has greater health years in total than x, z has greater health years in total than y, and yet x has greater health years in total than z. Next, let's move on to matters of value. To what extent does each measure satisfy a set of potentially desirable properties? The first of these properties is that the measure assigns equal value to current life expectancies of identical length, regardless of health-related quality of life. Another property is that it assigns positive value to health-related quality of life improvements during current life expectancy. Next, does the measure assign equal value to identical periods of life extension regardless of health-related quality of life? And finally, does the measure assign positive value to health-related quality of life improvements during life extension? Recall that the motivation for the health year in total approach is to overcome two specific issues, and those are that the QALY fails to satisfy 2a, while the equal value life years gained fails to satisfy 2b. Yet we find that none of these approaches satisfy all of these potentially desirable properties. In common with the QALY, the health years in total fails to satisfy 1a and 2a. The equal value life years gained fails to satisfy 1a and 2b, while the life year fails to satisfy 1b and 2b. The key point is that it is impossible for any measure to satisfy all of these properties simultaneously. In conclusion, the equal value life years gained and health years in total approaches are not viable alternatives to the QALY. Both have logical flaws. The equal value life year gained may result in dynamic inconsistencies, while the health years in total violates independence. Since no measure can satisfy all potentially desirable properties, Decision makers should consider which properties they value most, and then adopt a logical and consistent approach that satisfies these properties. 2 references were used in this presentation. The equal value of life years gained approach is outlined in the report by ICER, while the health years in total approach is outlined in a paper by Basu and colleagues published in Value in Health. Thanks for listening to this presentation, and I'd be happy to answer any questions you might have.